Okay, so here's some Sage code that I'll have linked in the text file linked in somewhere, Blackboard. And what this does, it solves the heat equation here, U sub T equal alpha squared U sub xx with homogeneous boundary conditions and an initial condition f of x on 0, 1. So we create some symbolic variables just so you can kind of see what's going on. I set alpha. This is, I don't remember what this is for. I'd have to look it up. I got this from Wikipedia for some different coefficients. I don't remember what it was, but it's some material. Could be water. I don't know. An initial condition. Now this is actually your textbook. One of your exercises uses x times 1 minus x or x minus x squared, which is just a parabola going through x equals 0, x equals 1, and opening down. Has a height of 0.25. And so then well, you need coefficients. Given an f, you need coefficients. Here I do the integration. I actually do numerical here. When it calls this, it will have a value for x and t, so it'll just do that. But we'll maybe take a minute to look at this integration for a couple other things, just so you can see. That's just the formula in the textbook. The 2 times the integral of the initial condition phi or f times sine n pi from 0 to 1, and this just decides what n it is. Again, this doesn't get called till down here, so it actually knows what x is, because I give it x when I define u here. And so this is the formula, the general formula for u. It's got the e to the, now this is, oh actually, this is, what the heck? I may need to change something here. This is 2k. I seem to be going up by odds here. I'm not sure why I did that. Let me fix that right now. So this should just be a k. Well, we'll see what happens here, because this should be k. And this should just be a k. I hadn't noticed that I had messed with that, but okay, so there we go. Much simpler looking now. I used k instead of n to sum, and I only sum 1 to 4. Now the reason I was doing that, although now it may do better, the reason I was doing that was partly because of how many x values. So here I do x, this is, notice I goes from 0 to 20, and I take I and I divide by 20. So what this is doing is it's splitting the x-axis up into 0, 0.05, 0.1, 0.15, or 0.15, and so forth up to 1. So it's just doing 20 intervals over the interval from 0 to 1 on x. And then this is times 0. So notice I'm here, this is t, it's u of 0. And then I do S1, I did 0.1. You could use any time you want. I'm using 0.1 and then 0.2. And so I make the, I evaluate things numerically, get the solution, and then I plot it, and You can see the output here for the different things. Blue is time 0, red is time 0.1. And so again, that's what we've seen before, is if the boundary conditions are 0 and I start out here with this heat up like this, well, it should just eventually, reduce down to 0, where all the heat diffuses to be equal to 0 along this thing, and so we see that happening. And here are coefficients, and notice, see, here's the k equals 1 coefficient, or n equals 1 coefficient, 0.25. But notice the next coefficients are all quite a bit smaller. So, less than 0.1, 0.01, and just gets much smaller after that. So you see that's the note, that was note 3, I think, in the notes, was that, it's really this first coefficient that tends to dominate for quite some time. So let's try evaluating this, see if it still looks okay. Because like I say, I didn't go by ones, I was going by other stuff. But yeah, so it looks fine. So I fixed that, and it'll be the right code for you. But now we'll try upping it a bit. So this just used the first 4 terms. So let's try going, when I went to the first 5 terms, so I changed this to a 6. It made that third plot really ugly. Let's see if it does this time. May or may not. Because I changed things. Yeah. See, so it still looks okay. Let's try to go up to like 10 terms. It'll be a little slow. But what I'm looking for is for it to all of a sudden not look smooth anymore and look really ugly. And it still may not, because the coefficients may be okay, but we'll see. Yeah, so notice here, see how ugly, what happened, it's not smooth. Well, the problem is that I'm only evaluating at every 0.05. Well, and if k here gets big enough, you see what happens is I start just sort of evaluating my function at very particular values of sine, and in which case some of them are things like sine of pi over 2, sine of pi over 4, sine of pi, sine of 2 pi, those kinds of things. And so what happens is it's no longer able to do a nice smooth interpolation going across here, because I'm not using enough points in here when I evaluate the function. And so I would need to run this up to like 40 or something instead of 20 in order to keep this smooth. But I can, so I'll go back to doing the first 5, because that works just fine now. It didn't before, because I was only doing odd k's for some reason. I don't remember why, but it probably had to do with just checking the code out at some point. But there we go, all nice and smooth again, and we see that it's just diminishing down to 0. We could, instead of looking at 0, 0.1, and 0.2, we could try looking at 1. Oops, I need to change it here. That's just the comment. So I'll change it here to 1, and here to a 2. So you can just do that to get different times if you wanted to. I evaluate, and these should look a lot shorter now compared to the very first one at time 0. Oh, and Well, that's interesting. So that looked really bad again because I'm just doing too many. So let's take this back down to just 4 of them. Try that. But part of the problem is I'm up at a higher time. So let's see if that fixes it. But if you get something weird like that, you know, where all of a sudden it just looks really crappy, it's because, there we go. It's just because you're not evaluating at enough values of x down here. And so there's a balance between you know, how many coefficients I do here. I just did 1, 2, and 3. I just did 3 coefficients. You know, so the number of coefficients you do here, and how many subintervals you use on the axes. So, you know, it makes it pretty smooth. I can tell what's going on. But again, I can't use too many subintervals. Or sorry, can't use too many of the functions. So if I want to take this, you know, if I want the time to go that far, like 2 seconds, and I want to have more coefficients here, I'll have to use more time and divide by a bigger number here and change those. Okay, so I could do that. So it's really this last one that's the problem. So I'll just change that one to 40. 40, so it's twice as much, and should look pretty good now. Even if I go here to, we'll do the 6, so instead of 3 terms I do 5. I think that'll work. And since the first 2 looked okay, I figured I would only up the number of values in the last one. Still doesn't look good. See, so you know, so that's a problem going there. It may, I guess it may simply be, I haven't thought about it too hard. It may simply be because I'm dividing by 5. You know, it could be that 5 is the bad number here. Could even be that 4 is. Let's try it with just 4. But again, you know, if things are not set quite right, yeah, see, so it still looks bad. So let's try another fix. Instead of 40, let's do something like 31. And 31 here. Now why 31? It's a prime number. And so I'm a lot less likely to, so I've got issues right now. I set that to a prime number. So these are just things to think about, you know, for numerical work. So let's see if that works by changing that to a prime, so that you don't get the same kind of division. May or may not work. No, still didn't do very well. You know, we could sit here and experiment all day. You know, I could try it with a smaller prime, you know, like 11, just to see what happens. But again, the issue has to do with where it's evaluating, not what the solution actually looks like. And so it's just, yeah, it's just doing a very poor job evaluating. So I'd have to look at it, and maybe I'll make a note at some point. But so we're probably best off just, you know, looking at the first 3 coefficients, going ahead and making this 20 if we want to go out that far. Again, this is going out to a 2 seconds instead of just 0.2. So, you know, again, that's part of the problem. You know, numerical stuff is, you know, you may think that the analytic stuff with all the algebra is so hard, but actually, you know, when you're dealing with computers and round off and various things like that, the numerical stuff can be just as nasty to try to figure out. And so, you know, here we've made it work for 2 seconds. But again, originally it was just the 0.1 and the 0.2, and it did just fine even with, I think, 4 or 5 terms there. But you know, there we go. So, but there, you know, you can see what the solution is doing, and so we have that. So that's this code. I'm going to do another quick video just to look at the coefficients here for a minute, but that's this code. So we'll stop that there.